Hi everybody, so in this video we'll be talking about transformations. So in algebra, a function matches each x value from the domain with a y value from the range. Similarly, in geometry, a transformation is a one-to-one correspondence or mapping that matches each pre-image point S to an image point S prime. So for example, if we're told that we have a function of x that's equal to 3 minus x cubed, and it matches x equals 2 with y equals blank, all we need to do to figure out what the y value is plug in the x value of 2 everywhere that we see x in the function rule. Okay, so here we have f of 2 is equal to 3 minus 4. So we have f of 2 is equal to 1. We were able to find what the corresponding y value was for the given x value. Similarly, with our transformation, we can find the image point that corresponds to the pre-image that's given. So here we have a translation of 2 to the right and 3 down, and we need to find what the image of p1 comma 4 would be. 2 to the right means we're adding 2 to the x-coordinate because we're moving 2 more towards the positive numbers. So 1 plus 2 would give us 3 for our new x-coordinate, our image x-coordinate. And 3 down would be taking away 3 from the y value because we're going 3 towards the negative numbers. 4 minus 3 would give us 1. So our corresponding image point to 1 comma 4 under the given translation would be 3 comma 1. Over here, take a look and try to guess which transformation each of the following images depicts. Use the word bank to help you. For the first image, we see that we are just sliding the image over to a new spot. Anytime the pre-image got to the image by sliding over, we have a translation. So we can indicate this as a translation. Translation notation is a capital T. And the coordinates of the translation, how much we're moving over to the x-axis and how much we're moving up or down on the y-axis. On the second image, we have a reflection. Notice that we have our line of reflection, that's the dotted line over here, and we have the mirror image of the bunny face when it's reflected over the line. So that's a reflection, and we indicate a reflection with a lowercase letter. And then next to the lowercase letter r, we put what the line of reflection is, what the line is we're reflecting over. So I'll write y equals question mark because that depends on what the line that we're reflecting over is. Here, it kind of looks like it could be the y-axis. So just so you can see better what this notation would look like, I'm going to write a reflection over the y-axis. Oh no. For the next image, we have a rotation to get from the pre-image to the image. The bunny face was rotated, and it looks like it was rotated in a counterclockwise direction. So not clockwise, but the opposite direction, which would be counterclockwise. We indicate our rotation with a capital R, and next to the capital R, which stands for rotation, we usually put the angle of rotation and the center of rotation. So once again, we usually put the angle of rotation. I'll indicate that as theta, whatever the angle that we're rotating at is, and the center of rotation, whatever the point is that our rotation is centered at, is happening at. And then finally, we have a dilation for the last image. A dilation means making something bigger or smaller. So the bunny here was made bigger from the pre-image to the image. So that would be a dilation, which we indicate as capital D. And dilations have a scale factor, and that scale factor is usually indicated as K. So, for example, if the dilation was by a scale factor of 2, if the pre-image was doubled to get the image, K would be 2. If we were making the image half the size of the pre-image, we would put 1/2 for K. And just like rotations, dilations also have a center of rotation. So the center of dilation, the center at which the dilation is happening at. If you don't see the center of rotation or the center of dilation given to you, then we can assume that it's centered at the origin. So that's also something to keep in mind. There is no translation that maps triangle ABC onto triangle A prime, B prime, C prime. This is instead an example of a line reflection. So a line reflection is kind of like a mirror image. You have a line of reflection that you're reflecting over, and you get the mirror image of the pre-image on the other side of the line of the reflection. Now, something important to keep in mind is that when you're doing a reflection, the points of the pre-image and the image are equidistant from the line of reflection. So point A to the line of reflection should be the same as A prime to the line of reflection. B to the line of reflection should be the same as B prime to the line of reflection. And C to C prime, here it's the same, it's at the same point, should be the same to the line of reflection. So it says, what is the image of PQ under a reflection over the x-axis? So in order to reflect PQ over the x-axis, we need the mirror image of each of the points P and Q. So to the line of reflection, there are 1, 2 spaces from P to the line of reflection. So I'm going to count 1, 2 spaces from the line of reflection to P prime. Equidistant from the line of reflection. That's what the image point and the pre-image point should be. So once again, for Q, it's 1, 2 spaces to the line of reflection. So 1, 2 spaces from the line of reflection should be Q prime. And there we have it. We have P prime, Q prime. The reflection of PQ under a reflection in the x-axis. This question says to transform triangle ABC as directed below. And it's giving us 2 transformations to do, and it says to do them both on the same coordinate plane. So in part A, it says to take the points x, y, and to do the following transformation. Take the x coordinates and add 2. Take the y coordinates and make them negative. So take a second, pause the video, and do the transformation. For each of the points, take the x coordinate and add 2 to it. And for each of the y coordinates, just make it negative instead of what it is. So change the sign from what it is to the opposite sign. Here is the image of triangle ABC under the transformation x plus 2 negative y. Pause the video again and do the transformation of ABC under the transformation x over 2 y plus 5. And here we have A double prime, B double prime, C double prime, which is the image of triangle ABC under the transformation x plus 2, y plus 5. Which of these 2 transformations maintain the size and shape of the original image? The answer is A. It moved around from triangle ABC to triangle A prime, B prime, C prime, but the size and shape remained the same. From triangle ABC to triangle A double prime, B double prime, C double prime, the triangle actually got smaller. When we talk about transformations, we talk about something called a rigid motion. So a transformation is considered to be a rigid motion if it satisfies the following conditions. So the first condition is that distance is preserved. For example, the distance from AB on the pre-image will be the same as the distance from A prime B prime on the image. The second is that angle measure is preserved. So an angle on the pre-image will be the same as the corresponding angle on the image. A figure is always congruent to its image, so that's the main defining property of a rigid motion. A transformation is considered a rigid motion if it produces an image that is exactly congruent to the pre-image. Collinearity is preserved. So if 2 points are on the same line before the transformation, they will be on the same line after the transformation if it's a rigid motion. And finally, midpoint is preserved. So if a point is the midpoint of a line segment before the transformation, it will also be the midpoint of the line segment after the transformation if the transformation is a rigid motion. Think to yourself, which transformation is not a rigid motion and why? If you said dilation, you were correct. A dilation is not a rigid motion because it does not produce a shape exactly congruent to the original. When you dilate a figure, you either make it bigger or smaller. So if this is our pre-image, the dilation, the image could be bigger. If this is our pre-image, the dilation or the image, the dilated figure or the image could be smaller. So a dilation does not produce an image that's exactly congruent or exactly the same as the pre-image. Take a second and answer the following questions. What kind of transformation is shown in each of the following images? If you said rotation for A, you would be correct. And specifically, that is a rotation of 90 degrees. For B, if you said reflection, you would be correct. I don't know exactly what the line of reflection would be, but it would be equidistant from both the pre-image and the image. Here we have a dilation. I don't know exactly what the scale factor of the dilation would be, but I see that it would be some kind of positive number because we are making the pre-image bigger to get the image. And then finally, here we have a translation. I don't know exactly what the translation would be because I'm not on a coordinate grid here. But I see that we are moving either down and to the right or moving to the right and then down. Either way, we are increasing the x coordinates and we are decreasing the y coordinates. For number 2, it says find the coordinates of the image of P1, 2 under a reflection in each line. Take a second, see what it is, and then you'll get the answer. Here are the answers. Keep in mind that basically what you're doing when you're doing a reflection is you are making sure that your pre-image point and your image point are equidistant from the line of reflection. So if we're reflecting over the x-axis and we're starting with the purple point P, since it's 2 spaces from the x-axis, we want to make sure it's brought 2 spaces on the other side of the x-axis. If we're reflecting over the y-axis, it's 1 space from the y-axis, so we want to make sure it's 1 more space from the y-axis to get the image point. If we're reflecting over the blue line y equals 3, it is 1 space from the line y equals 3, so we want to bring it 1 more space to the other side of that line. If we're reflecting over y equals 2, the green line, well, it's already on that line, so the reflection will be in exactly the same spot. And finally, if we're reflecting over the red line, y equals x, it's like 1 diagonal space from the line, so we want to move it 1 diagonal space to the other side of the line, to the point 2, 1. Pause the video and try out these 3 practice questions. Here are the answers. Take a second, pause the video, and check your work. Let's end our video by answering the following questions. In your own words, what does rigid motion mean? Which transformation is not a rigid motion? Please explain why.